All right, before we get into the notes about isotopes and radioactivity, there are a couple of things that we want to review. The first is remembering what two atomic particles are found in the nucleus and give the atom mass, and those are the protons and the neutrons. Those are going to be the most important aspect for these notes. Electrons, while they are really important for bonding, they don't really play a role in isotopes or radioactivity, so we're going to be focusing on the protons and the neutrons. The second thing that we want to review is the idea of that it's the number of protons that are going to determine what type of an element it is, and that changing the number of neutrons, because they don't determine the element type, even if you have more or less neutrons, it's still going to be the same element. It doesn't change that type because the neutrons aren't the deciding factor. It is the protons. Okay, so with that, we're going to start talking about isotopes. So an isotope is when you have two atoms of the same element that have a different number of neutrons. Now again, it's the number of protons that determine the element, not the neutrons. So we can change the number of neutrons while still keeping the atom the exact same. However, while it doesn't change the type of atom you have, it does change the atomic mass. So this is going to cause them to have different atomic masses. In our example here, we have an atom that has 6 protons and 6 neutrons. This atom here still has 6 protons, so it's still the same type of element, but it actually has 7 neutrons, so it's going to have a slightly heavier mass. And then the final one, there's again still 6 protons, but there are 8 neutrons, so again the mass is going to be increasing. Since the only difference between isotopes is the number of neutrons, they can be identified by their specific mass number. We're going to write the notation for those. The way you write the notation for an isotope is you write the element symbol, then you just put a small dash, and then write the provided isotope mass. So let's do an example here. In this case, if we have carbon-12, so 6 protons, that's what makes it carbon, and 6 neutrons. The isotope notation is going to be C for carbon-12 because the mass is 12. Carbon-13, however, has 7 neutrons with the 6 protons, so its notation would be C-13. And carbon-14 has 8 neutrons, and so it's going to be C-14. Now, all 3 of these are carbon, but they do have different masses. The way I like to think about it is think about siblings. You're the same family, but you're slightly different, right? So they're all carbon, but they have slightly different masses. So siblings are all in the same family, but they may look slightly different. Some might be taller, some might be shorter, but still technically they are the same family. Now, that was going based off of a picture where we could actually physically count the protons and neutrons. You can also figure out how many neutrons there are from the isotope notation. If you're given the information about an isotope, you can use it to calculate the number of neutrons of that particular atom. To do this, you simply subtract the atomic number, so what determines the element type, or the number of protons, from the isotope mass. What's important here to remember, though, is that you're doing the isotope mass, not the mass that's on the periodic table. Remember, the mass on the periodic table is the average of all the different isotopes combined. So you have to make sure you're looking at the particular isotope mass when determining your neutrons. So this is going to lead us into radioactive decay. Radioactive decay is the process when an atom's nucleus releases a particle and energy. This is what we call radiation. Okay, this is where we got the idea of radiation is from radioactive decay. So the two things that are released when an atom undergoes radioactive decay are energy and some form of particle. This also causes the atom to change from one type of element into a completely different element. So what causes this radioactivity? The radioactivity within an atom is caused by the addition of neutrons into the nucleus. So adding those extra neutrons to the carbon-14 atom makes the nucleus unstable. It's like there's too many neutrons for the atom to be able to hold the nucleus together, and so it becomes unstable. So carbon-12, the nucleus is fine and stable, and it's not radioactive. Carbon-13 is also stable and not radioactive. But when you get to carbon-14, there's too many neutrons for the nucleus to be able to stick together, and so that is a radioactive element. Now there are two different types of radioactivity that we're going to focus on: alpha decay and beta decay. The first is alpha decay. Alpha decay is when the original unstable nucleus, called the parent nucleus, is going to break into two pieces. It's going to break into what is called the daughter nucleus, which is the nucleus that is created. Okay, it's going to be called the daughter nucleus, and release an alpha particle. Okay, an alpha particle is made up of 2 protons and 2 neutrons. So we start off with one unstable parent nucleus, and then when it undergoes decay, it releases the alpha particle, the 2 protons, 2 neutrons, and is left behind, and the daughter nucleus is left behind. So this large nucleus splits into 2 separate pieces. Since both neutrons and protons are released, both the atomic number, right here, changes, and the atomic mass also changes. The atomic number of the nucleus, of the daughter nucleus, will go down or decrease by 2, and the atomic mass will decrease by 4. Another way of looking at it is that after an atom undergoes alpha decay, the atomic number, you're going to take the original atomic number, so in this case radium-88, and subtract 2 to find your new element, which is radon. And then you're going to take the original mass, in this case the original mass of our isotope was radium-226, so we're going to take that atomic mass and subtract 4 because it lost 2 protons and 2 neutrons. So my new element is radon-222. So you're going back 2 places on the periodic table and subtracting 4 from the mass that you are given, not the mass on the periodic table, the mass that you are given. So let's do a practice one. So we're going to say what happens when Sg263, which has an atomic number of 106, what will it become after undergoing alpha decay? So the parent nucleus is Sg263, and we want to know what the daughter nucleus is going to be. So first we have to determine the new atomic number. So we're going to take 106, which is the atomic number, and subtract 2. So that's 104. And looking at the periodic table, we can find that 104 is Rutherfordium, Rf. So we know that our daughter nucleus is going to be Rf something. The second step is to find the new atomic mass. We're going to do that by taking the 263 that we got here, that we were given, and subtract 4. So that becomes 259. So our new element is Rutherfordium-259. That's going to be our daughter nucleus. So that's alpha decay. Beta decay is similar in that, once again, you have a parent nucleus and a daughter nucleus and a particle. But in this case, with beta decay, what happens is a neutron in the nucleus releases an electron, what's called a beta particle, turning the neutron into a proton. So a neutron becomes a proton when it loses an electron. Because this happens, the atomic number of the daughter nucleus actually goes up. It increases, but the atomic mass is not going to change at all. Okay? The atomic mass stays exactly the same. So we go of our daughter nucleus, the atomic number increases by 1, but the atomic mass stays identical because a neutron became a proton. They are still the same mass, so the nucleus itself did not lose any mass. So in this case, we're looking at polonium. Okay, if we had polonium-218, we're going to take the original atomic number and add 1, so it becomes astatine, and we leave our mass completely alone. We don't change the mass at all. So we go from polonium-218 to astatine-218. So let's do one more example here. What will sodium-24, atomic number 11, become after undergoing beta decay? Again, first we're going to determine our new atomic number. We're starting with 11, and we're going to add 1, so it becomes 12. So our new element, the daughter nucleus, becomes magnesium. And our mass, there's no change, so our final element is magnesium-24.